All right, so for the rest of the proof, again, we have this. We just proved 2. Now we're going to prove 3, 4, and 5. So let's start with 3. If we have an intermediate extension, then the order of, the degree of L over M is the order of the corresponding Galois group of L over M. And then we have the degree of M over K is the index of the Galois group of L over M in G. Okay, so let's prove that. This will not be hard. For 3, K contained in M contained in L, and L over M is finite normal. Why is it finite normal? Well, again, L over K is finite normal, so L over M must also be finite normal, because L over K is a splitting field, so L over M is also a splitting field. That was a homework problem. Okay, so by 1, for finite normal extensions, by 1, the degree of L over M is the order of the Galois group of L over M, but the Galois group of L over M is what we mean by M star. Great. Okay, so that was one of the parts. The other part is look at the Tower law. So by the Tower law, the degree of M over K is the degree of L over K divided by the degree of L over M. If you work that out, you'll find the Tower law will tell you this. This upper guy is the order of the Galois group by part 1. And by what we just did, this is the order of M star, the Galois group of L over M. All right, so that's that. Now we need to take an intermediate extension that's normal, or an intermediate extension, we need to show it's normal if and only if the corresponding subgroup of the Galois group is normal. Let me just give you a quick reminder. We proved in this lemma that if we have any field extension and any element of the Galois group in any intermediate field, then tau of M star is tau M star tau inverse. So when we conjugate, that is when we check for normality, it corresponds to applying tau to the intermediate extension. Okay, so for 4, we're going to suppose M over K is normal. It's normal and finite. We know, and show that the subgroup of G is normal. So how do we do that? We need to show tau M star tau inverse is contained in M star for all tau in G. So take some tau in G. Then what do we know? Well, tau restricted to M. Well, tau is a mapping from L, of course, to L. And we can restrict that to M. So tau restricted to M is a mapping from M to L. But M over K is normal, and you cannot escape normality, right? So by normality, these are sort of algebraic boundaries. Tau restricted to M has image M as well, because normal extensions are algebraic boundaries. Okay? So tau of M star is just equal, tau of M itself is just equal to M. By the lemma, M star, which is tau of M star, is tau M star tau inverse, and that proves the normality condition. All right, now we need to suppose that the subgroup is normal. All right, thus let me conclude M star is normal in G. Suppose that M star is normal in G. We show M over K is normal. All right, let's let sigma from M to L be a K monomorphism. We didn't prove this in chapter 11, but if we can show that we cannot escape sigma, or sorry, if we cannot escape M, then it is also normal in this situation. Okay? We can, since L over K is normal, we can extend sigma to some tau from the big field L to itself. We talked about this, various different forms for most of the second half of this class, but we did this in chapter 11. And this guy is an extension. So tau restricted to M is, of course, sigma. Then what do we know? Well, since it's normal, when we apply tau and when we conjugate the subgroup, the normal subgroup by tau, we actually get M star out of it. Okay, so tau, M star, tau inverse is M star. But by part 2 of the theorem, let's scroll up here for a second, star and dagger are bijections. So on the one hand, this is M star. On the other hand, we know it's tau of M star by the lemma, but star is a bijection. So M must be equal to tau of M. But tau restricted to M is just sigma, and so we're not able to escape M. M over K is normal. Extensions that you cannot escape are normal in this situation. All right, so that's the proof of 4. And then lastly, let's go up to part 5, the very last thing we're going to do in this chapter. Suppose we have a normal extension, then we can do this sort of cancellation. Right? If you are familiar with the isomorphism theorems from algebra, this is sort of like, I forget what it's called, the third isomorphism theorem, I don't know, where you sort of cancel the L's. Okay. All right, so let's prove that guy. For 5, let's let M over K be normal. G prime, the Galois group of M over K. This is the guy we're going to try to identify as a quotient of G. And we're going to define a mapping phi from G to G prime. Okay, again, G is the Galois group of L over M. And we're going to define it by, all right, so we need to take an automorphism of L. Okay, so tau is an automorphism of L. And we're going to just do a restriction mapping. We're going to restrict to M. When we do that, when we restrict tau to M, since M over K is normal, tau of M has to be M. You cannot escape normal extensions. So tau restricted to M is, in fact, an automorphism of M. It would be bad if it wasn't normal, you could leave. Okay. All right. Since the operation in G is composition, and G prime is also composition of functions, phi is a homomorphism of groups. It is surjective because for all sigma in the Galois group of M over K, we can view sigma as a mapping from M to M, of course, but we can then include M back into L and then extend to some tau from L to L, that such that tau restricted to M is sigma. So by those extension theorems that we prove, this mapping is a surjective because we can always lift an automorphism from M to M to one from L to L. So it's on to, great. What's the kernel? Suppose phi of tau is the identity on M. Right? So what's the what's the trivial element of G prime? It's just the identity, the guy that's the identity on M. So what automorphisms of G don't become the identity when you restrict to M? Excuse me. Well, it's exactly the elements of the Galois group of L over M, the automorphisms of L that fix M. So the kernel of phi is precisely the Galois group of L over M. And we have, by the first isomorphism theorem, or by the Noether isomorphism theorem, whatever you like to call it, G mod the kernel of phi is the image, because it's onto, the image is everything. But all this is saying is it's saying the Galois group of L over K, which is G, mod the kernel, which we've identified as the Galois group of L over M, is the image, which we've G prime was just notation for the Galois group of M over K. And that completes the proof of the fundamental theorem. And again, this is kind of confusing. We don't have any examples. I haven't presented you with a lot of examples here besides the one we've seen in the previous chapters. But we'll get to a wealth of examples in the next chapter.